I'm live. I think it says live. I should probably trust it because it says live. Why would StreamYard lie to me? I don't know. Hey, there I am. Weird. It's like I'm watching myself through the internet. Like Robception. Really, really weird. Well, howdy, space campers. This is the Rob, and this is a trial of a live stream. And so I'm going to minimize that. In a lot of ways, this is me running before I walk. I guess. Sorry, I'm looking at live viewers. Apparently, there are two. Me twice. Okay. So I'm guessing nobody is watching this at the moment, but that's quite all right because, as the title implies, this is a trial. So if you have not checked out any of my other content, please feel free to, particularly Rob World Episode One. It kind of explains who I am and what I'm about. What these live streams are intended to do is basically it's a platform. Honestly, I'm not entirely certain. So the goal at this point is to do probably a bi-monthly or twice a month. I can never figure out if bi-monthly means once every 2 months or twice every month. I don't know. Thinking twice every month. Let's go with that. I will do one of these, and it will be either me interviewing someone or speaking with someone in the community, or either the YouTube debunking community, or someone in the science education community, either one of my colleagues or friends of mine who are educators, particularly in science, and just have them on and shoot the stars, as it were. Just talk about things that are relevant to science communication, specifically how do we deal with educating both people who are willing, such as students who come to class, and those who are unwilling, either students that don't come to class or, even worse, people who deny the subject actually exists at all. And so that's one of the goals of these live streams, is to provide that sort of platform. And the other, obviously, is I have access to one of the largest teaching telescopes on the eastern seaboard of the United States. And I would like to have the opportunity to be able to share that with you as much as I can. Now, my institution, George Mason, does do public nights. We don't do them over the summer, but oh, hi Tusk. Uh, I'm actually explaining what all of this is about. So my institution, George Mason, does public nights, not over the summer, but during the fall and spring semesters, and so I will be advertising those. But I'd like to just do my own sort of private tours of the observatory whenever I can, and whenever the instrument is free for me to do so. And so that's the other reason for doing these bi-monthly, twice monthly live streams. Um, so, and yeah, Tusk, this is a complete trial. I have no idea what I'm doing, so I just kind of wanted to see what live streaming was all about. Um, I uh, I'm currently in the middle of editing my second episode, which at this point is around 30 minutes long, and I still have work to do on it because, yeah, just a lot of it always seems to, I don't know why, but when I get into making the content, it just seems like it expands the space allowed. It expands the time allowed. I know that it's probably applicable to a lot of things. You pretty much can, with a creative project, you can throw as much at it as you want. You never seem to have enough time to complete it. So at some point, I will just have to punt and actually get the thing out the door. Because at this point, it's been a month, if not more. So, yeah. Okay. That Post-it note can go bye-bye. What's next? Oh, update on the channel. Yes. So, the channel in general, what I hope to be able to do, again, time committed or time dependent, is probably every other week that I don't do the live stream, I will produce a Raw World episode where I talk about some astrophysical event or some astrophysical phenomenon, such as Kepler's laws or black holes or the Big Bang, things of that nature, and explain not only what they are but also what they aren't, and try to battle some misconceptions that folks might have among the popular community or the layman community, in order to, because my goal is or my raison d'etre, as it were, is to combat science denialism in all of its forms. Etty, I don't think I've heard her name pronounced out loud, so I hope I'm pronouncing that correctly. Eddie's channel. Sure, yeah. I would be happy to be on her channel if she wants to be on. So, yeah, we should probably hook that up over Discord at some point. And if she wants to come over onto mine, or if you want to come over onto mine, that works for me as well. Although I have no idea how one actually does that. Excuse me while I whip this out. That one. All right. Now I've got Discord up. Where was I going with that? So yeah. So once every couple weeks, I will put out a Raw World episode, which is just a presentation, as it were. I hesitate to use the word lecture. Hopefully, it's more interesting than that. I will present on a astrophysical topic and try to make it as interesting as humanly possible. Another thing that I would like to do, probably weekly, is a news program of some sort, something where I talk about the essentially space news. What is currently going on with SpaceX? What are the robots on Mars doing? Things of that nature. And in addition to that, providing my hot takes on people that irritate me, like Neil deGrasse Tyson and Elon Musk, and people who boggle me, like Dr. Jason Lisle. I bought this used, by the way. It also has a nice inscription, which is written in dark ink on a dark page, which to me is apropos of the subject matter. What this is, taking back astronomy, is a astronomy textbook from a creationist point of view. Now, young Earth creationism boggles my mind to begin with. But if one assumes that the Earth is flat, or if one assumes that, if one assumes the Earth is flat, then your ability to ignore mainstream science, or your issues with mainstream science, I should say, are pretty significant. So for me, that logic somewhat holds. Dr. Lisle, and he is a doctor. He's not Kent Hovind. He actually got his PhD from Colorado Boulder. He is an astrophysicist who did his dissertation work on supergranulation in the sun. The idea that someone who has studied the subject matter can still believe the Earth is only 6,000 years old boggles my mind. I literally do not understand how that is a thing. Although, spoiler alert, I think I know his reasoning for his logical way of escaping certain things, such as starlight travel times, the fact that it actually takes light about 1 million or so years to get from the center of the sun where it's generated out to about 70%, well, really, at that point, all the way out of the sun. There are a lot of quite literally astronomical timescales that he has to ignore and or reconcile. And I think the way he's going to do it is by just basically saying God made it that way. And so I'm going to review his book and let you know what try to give you it as an objective a as an objective a take on it as I possibly can. So yeah, not quite a debunk, as it were. Well, it will be a debunk as well, but I like reading, and so I'm going to debunk books as opposed to debunk videos. It's kind of be my hot take on things. So, um, so yeah, okay. That out of the way. All right. Let's see. Um, yeah. Okay. Let us see if I can actually share a screen. Howdy. Yeah, I know we've interacted before, but I am just absolute crap at names. Pramono, Pramonini, Pre-Ulti. That's what I'm going to call you Pre-Ulti unless you tell me that's not going to happen. So, Pre-Ulti, how you doing? You missed my spiel, or I don't know if you saw my spiel at the beginning or not, but welcome. I just kind of went over what I hope to do with with these live streams and such. This is all, like I said, very new. A little bit nervous, to be honest with you, because it's just weird, kind of talking into. Oh, that actually makes sense. First name, last name. It's kind of weird talking into a box and only getting text and response. Uh, I guess I'll figure it out. I'll figure it out. Well, you're in time because I'm going to give I was planning on. One of the things I wanted to test out was the ability to share screens and do all that kind of good stuff. And so I'm going to give a closed dome tour of the George Mason Observatory. The reason why it's closed dome is because I know you can't see it on here, but there is water all over my window because we just had a rainstorm passing through here, and there ain't no way that I'm going to possibly open up the dome if there is even a speck of chance that there is rain within a 30, 40 kilometer range. Yes, we have been rained on before. No, it's not good for the telescope. Water, glass, not a good mix. So, all right. Oh, engineering marvel. What engineering marvel? You have those in Scotland? All right. I will see Tusk. I will hopefully talk to you later, and yeah, you can catch up with if you want. You obviously can catch up on this later. This will be posted onto the tubes. The Falkirk wheel. Oops, nope. The Falkirk wheel. I will have to Google that. No idea what that is. I have no idea where that is, other than somewhere in the British Isles. But that's kind of an educated guess, considering where you are. And it's called Falkirk. So, all right, let's see here. What can I do? Share. Share screen. Easiest with two monitors. No kidding. That will do. That one. You're on different monitors. All right. So this is the way that we use the telescope. So our telescope, one of the good things, as it were, that came out of the pandemic was that our time frame to allow for remote observing with our telescope got accelerated because of the fact that we were obviously in lockdown and classes were moving virtually. We still wanted to be able to provide students access to our observatory, and it is, I wasn't going to say more importantly, but in a tangent or complementary way, we also do undergraduate and graduate research here pretty much every night that we have a clear night. Dr. Peter Plavchan he does TESS follow-up. And what that means is TESS is a satellite which has been looking for signatures for exoplanets. And just simply because of the vast volume of stars that they are dealing with, TESS only has a limited amount of time to look at any particular object. And because science is the way it is, even if you get what looks to be a positive result within that window, we're not going to take that as an absolute fact. It needs to be followed up. It needs more observations in order to determine whether or not, yes, that is definitively a exoplanetary signature. And so that's where smaller telescopes like ours come in that the big guys like Keck, which are 10 meters, obviously they actually oversubscribed, meaning they have more people wanting to use the telescope than there are minutes in the night over the entire year. So there is this sort of work would be far too low on the priority level in order to be able to utilize the big ones. And so hence why we're getting into a very, very interesting age, particularly in terms of citizen science, as I like to put it. I don't like to use the term amateur astronomers or anything of that nature, because some of these folks you can call them a lot of things. Amateur is not one of them. They are just simply not astronomers by profession. So I refer to them as citizen scientists. And so we're getting into this really just exciting era, in my opinion, where detectors and telescopes are becoming sensitive enough and affordable enough that people can do this sort of work and actually fulfill a need inside the astronomy community that is opening up because of this gap or this disconnect between available research instruments and available research time. When it comes to follow-up observations, which are vital to determining whether or not exoplanets actually exist, to confirm the existence of future exoplanets are a thing. We do know that. But to define more of them, to get more data so that we can really classify how these things, how many rocky planets are there? Are there, how many gas giants are there? These water worlds, which we believe exist in other solar systems, but we do not even see within our own, which is just friggin' awesome. The idea that you have a planet that is somewhere in between the mass of the Earth and mass of Neptune, and instead of it being primarily gaseous, it's actually primarily water. And so it's literally a water world that Kevin Costner hasn't screwed up yet. So So yeah, so there are just amazing discoveries out there that citizen scientists can work on, particularly with with their own telescopes. And so that's we're trying to fill. We're moving into that gap. Another, and I know I'm rambling, but I don't care. Another really cool or really cool citizen science sort of project is, or a project that is well suited to this type of instrument, is something is work done by Dr. Misty Bentz. She's at Georgia State University, and she does what is called reverberation mapping. Now, what's really cool about this is there are these things called active galactic nuclei in the universe, and they are in the centers of, as you might guess, galaxies. What an active galactic nuclei is, very briefly, very crudely, is a supermassive black hole that weighs in at around millions to billions size, or the millions or billions of the mass of the sun. And this and it's surrounded by this accretion disk. It's surrounded by this disk of material, which is rubbing up against itself. Essentially, the inner parts of the disk are moving at much faster rates than the outer part of the disk, and some of that material is infalling into the black hole. It's literally eating the disk over time, and it produces a tremendous amount of energy. It produces so much energy that if you were to take that thing out of the galaxy itself and put it right next to it, the AGN would actually outshine the parent galaxy that it was located. So just one of, or the most, aside from, the Big Bang, the most energetic phenomenon that we know of in the universe. And so one of the projects that she's doing is she's attempting to actually directly measure the mass of those central black holes by looking at how essentially light reverberates through that disk. I mean, it's a fairly complicated process, and maybe that'll be an episode of Raw World where I'll talk about how to actually do that, or how that's actually done. But the thing is, again, what we're talking about is this type of work is very time intensive, and so you need a lot of well, you need a lot of time. You need a lot of time at a telescope staring at a particular object in order to get enough data in order to do this process. And again, long time sitting on one particular target for a long time, utilizing these larger telescopes, is really not profitable, as it were, because of the fact that there is so much subscription, there is so much, there are so many projects that need to get done. We have to basically prioritize, and the idea is to touch on as many different projects as we possibly can using the best instruments that we have, rather than just sitting on one particular object for as long as possible and going from there. So that's where telescopes like this one kind of come into the mix, because these AGN, these black holes, or rather the environments around them, are bright enough that our telescopes are able to see them and actually take the necessary measurements to do it. So I think I've rambled enough. So again, for if anyone is coming in late or looking at this, this is our observatory here at George Mason. And so hello, Reggie. So shouldn't galaxies be collapsing, like smaller and compressing, not further apart because of the mass? That is an excellent question. Now, the reason why galaxies do not collapse in upon themselves is the same reason why the moon does not collapse into the Earth. It's because pretty much everything in the galaxy is in some kind of orbit, and so it's perpetually in free fall. So the the disk of material surrounding that supermassive black hole is in free fall around the black hole. The stars around that, out in the outer parts of the galaxy, are all in free fall around that central black hole. So if everything in the galaxy stopped, if you could somehow just magically freeze everything, and so that the relative velocities between each other were zero, then yes, all of that would collapse in and upon itself. But because there's that rotational motion, you have these things in orbit, which allows it to be stable. What are we doing here? Yep, pardon me, I have allergies this time of year. So, wait, this isn't so big. That's what she said. Okay, I have no idea why that is doing that. So, oh, excellent, thank you. Glad that made sense. And I don't know what's going on with our #1 camera, but while it's trying to figure itself out, there it is. So, yeah, because of the pandemic, we accelerated our process of bringing everything online, and so we're able to essentially log onto the telescope's computer remotely. So, from where I'm sitting, this telescope is right up there. So it's about 3 floors above me. It's on the roof of this building, as you can see from over here. The other thing, hopefully, you can see is that the sky is slate gray, and that's because we just had a rainstorm. So I will not be opening up the telescope tonight because, as I mentioned, we've already had this. I have seen rain on a telescope, and it's heartbreaking. I don't have words for it. It's apocalyptic. And so up here, this is our 32-inch telescope, or 0.8 meter telescope. To give you a sense of scale, as it were, the largest telescopes in the world at the moment are 100 meters in size. So roughly speaking, this is 1/10 the size of the largest telescopes that we currently have in the world that view in the same optical range as the human eye. Obviously, radio telescopes are much far more larger, or far larger. This screen over here is the control room. So in the before times, or if people are just feeling nostalgic, they can go up onto the roof and actually sit here and operate the telescope, sort of quote unquote in person. This is the outside of the dome, or outside of our dome. We have the elevator bank over here. This is how you get to the roof, so forth. And then down here, the camera on the right, or bottom right, is looking at the, so if that is the telescope, so the light is coming in through here, and here is the black ring where all the camera is. Then the camera on the webcam on the bottom right is looking straight up this way. So this is what we refer to as the RA motor. It allows the telescope to rotate in this direction, or in right ascension, or stellar longitude. The reason why we have a camera there is very much like you see up here. This area, which looks similar, is the deck motor. That allows the telescope to tilt in this direction, or stellar latitude. And so we have those telescopes there mainly for maintenance purposes. If something were to, say, happen, if there was a failure of some sort, we have cameras on there, and they are motion activated. So if something were to happen during a remote observing session, that will allow the operator to actually sort of try to visually identify what something could break or what has broken and so forth. All right. So, speaking of telescope, what am I doing here? Oh yeah. Let's do. That is not the. Okay. It would help if I looked at the right computer screen. Yay! Rob can tech. All right. So the way that this works, the way that we can operate this telescope, is through a piece of software called Sky, and we should probably connect the telescope. And so the Sky, let's move that there. So you can totally control. Yes, yes. So from where I'm sitting, I can take control of the telescope, and I can basically tell it to go wherever I want it to go, and then take images. So, for example, apologize. This is not quite the way that I run things, simply because of the fact that the dome isn't opening. So let us just go there. Let's go to Alpheratz, which is in the constellation of Andromeda or Pegasus, depending on how you count things. And so it's literally just point and shoot. So I can click on an object in the sky, and I tell it to slew, and it will, in fact, slew. You can see up here in the upper left, although it's not updating very quickly. The upper left, you can see the telescope moving to point the telescope in that direction. What I don't have online, because again this is a closed dome tour, is the dome itself. The dome, you can see here from the profile that there's this over here. Yes, you can't see my cursor. This over here is a lower shutter that actually swings down, open and down, and then this upper part is the upper shutter, and that swings back. And then on top of that, and actually I can show this. Hopefully this doesn't mess things up. The dome can be synced to the telescope. So the concept of the astronomical dome is certainly not a new one. And actually, the concept of an astronomical dome predated telescopes. Tycho Brahe was the first person that I know of, or Tycho, as I've been recently corrected. Tycho Brahe was the first person to actually create an observatory using domes, even though his instruments were visual or naked eye instruments. They were basically just large sextants that he just sighted down using his eye. The reason for that is wind. He was the most phenomenal visual observer of his age. As far as I know, he has been unsurpassed in his ability to detect positions in absolute or in very precise terms. He was able to determine the position of a star in the sky to 1/30th the width of a full moon. That is phenomenal. So he actually created a dome. He had to put the domes around his instruments in order to block the wind. And so that's one of the reasons why we still use domes today, is in order to block the wind so the wind doesn't come by and rattle the telescope, causing it to vibrate. Obviously, the other reason is light pollution. So we are on a college campus, so there is a certain amount of light pollution. You can see that in the west, beyond the telescope, you can see that the sky is a bit bright. And so the dome protects against ambient light from streaming in. So I can sync the telescopes together, or sync the telescope with the dome, so that regardless of where I'm pointing, and let's go to Altair. regardless of where I'm pointing, the dome will, or the dome will track with the telescope, keeping that open shutter right in front of the telescope that it's pointing at. Again, it's updating. Now, the back end of this that's coming into view is where the instrument, basically our scientific instruments, are located. These are where the digital cameras are located. And let me make sure. Okay, good. So we use a pretty much just a more sophisticated version of the camera in your phone. So it's a what's called a charge coupled device, or a CCD camera. And so it's the exact same technology that is located in your phone, just on a little bit more sophisticated level. And that is what this black box right here is. Unlike the cell phone or camera, or the camera phone in the camera. Sorry. How much does it cost to maintain? That's kind of a hard question to answer, because there isn't a continuous cost. So the cost is, when things break, they can get expensive. So, for example, we recently had problems with our RA motor, and that cost us set us back a few hundred. One of the larger expenditures that is regular is you have to clean the primary mirror cell, and so this area encapsulated within this black ring, or supported by this black ring, there is a 32-inch mirror, which is slightly curved. It's actually curved to look like a hyperbola, hyperbola. So parabola, hyperbola. So it's very slightly curved. And as you can imagine, even given our best efforts, that mirror is going to get dirty. It's going to be covered in dust, things of that nature. So occasionally it needs to not only be cleaned, but it also needs to be resurfaced. And so that can set you back. I haven't actually seen the cost of that, but I would say that's probably a few thousand. But we do that every 3 to 5 years. So yeah, it's hard to put a cost on maintenance, because thankfully it's not an everyday occurrence that we actually have to do that. So with the camera, unlike, like I said, with the camera on your phone, the camera on your phone is a color camera. Obviously, when you point and shoot, you get a color image on the back end, and that is because of the way that the camera in your phone has been constructed. CCD cameras, and by CCD I'm just going to default. When I say CCD camera, what I'm talking about is a camera on a telescope. A CCD camera is, in a way, simpler in that it's a single chip and it's monochrome. And so it is sensitive to wavelengths of light which are slightly beyond the bluer end of what we can see with our human eye, or into the ultraviolet, out to just slightly past the red end of the human eye spectrum, or into the infrared. And so it captures the entirety of all of the light streaming through space with those wavelengths and those frequencies. And so if we were to just take an unfiltered image using the CCD camera, we would get a black and white photo which shows us all of the light which is coming through there. Now, for a variety of reasons, and again, I probably will do an episode on this in and upon itself, we astronomers will always take monochrome images, but we will filter those images. We will filter those monochrome images by using a filter wheel, and you really can't see it from here, but there's a black disc right in front of the camera, and in that disc are small squares of colored glass, which only allow certain wavelengths of light to go through. So we have a blue filter. For example, we have a blue filter, which is a blue piece of glass. It only allows light that is blue to pass through it. It blocks out all the rest of the light. We have a green filter. Again, it only allows green, blocks out everything else. We have a red filter and a few others. And what we can do is we can, or what we do is we take we take images from using those different filters, and not only does that allow us to create pretty pictures, which I'll show you in a moment, but it also has physical meaning. These wavelengths tell us what is, or allow us to peek at what is physically happening to that object. Oh, and we have sunrise. Woo! Oh, you can see that it's, yeah, currently 5:28 in the morning where I currently am. So yeah, so what do these images look like? Well, I'm glad I asked myself that question. What we do is we use a program called MaximDL in order to control that camera. So whenever we're set up on a target of interest, and just kind of going back to this, yes, we can pick and choose. For instance, if I wanted to go to Jupiter, for example, I can just pick it. I hit slew, and it will slew to that object. Or I can put in coordinate. I can also search. So, for example, I can do Ring Nebula in Lyra. I can find it. I can slew to it. Or if I know the coordinates, much like a city on the United States has a very specific longitude and latitude, stars and other celestial objects have very specific right ascension and declination. So if I know the right ascension and declination of the object of interest, I can just input that in there and go slew and go. And so I can point it out. So once it's pointed up, once it's where the telescope thinks it knows where it's pointing, and it's tracking at a sidereal rate, which is the rate at which the stars travel across the night sky due to the rotation of the Earth, the round Earth below it. Because of that rate is constant, and if you want to know what that rate is, it's divide 360 degrees by 23 hours 56 minutes. That is the sidereal rate. And at some point, I will do a Rob World episode where I describe the difference between a synodic day and a sidereal day. One is relative to the sun, and the other is relative to the stars, which probably is an anti-flat Earth proof somewhere, but I haven't really thought about it too terribly much. But yes, there are actually two definitions of a day. There is the day as defined by the motion of the sun, and then there is the day as defined by the motion of the stars in the night sky. So synodic, sidereal. So the telescope tracks at a sidereal rate. And so theoretically, the object of interest will be in the field of view of the telescope the entire time you want to look at it. And so we would then connect up. We can then connect up. I'm not going to do that because everything is shut down. But you can take images that look something like this. And now, here's the fun part. Does the Rob know where he puts stuff? Probably not. And also, does the computer know that stuff is there? Loading. So, oops, always get the times wrong. So you can see we've been at this for a while. George Mason has been at this for a while. We have been taking scientific data at this institution since 2013. And we have all of it. We have basically there are at this point we're getting into about 2 terabytes worth of data that have been taken over the course of this telescope's career. Most of it not by me, but some of it has been. Let's see if I can. Ah, yes, the precious. Um, let's see here. Let's pull that up. Actually, pull those up. Now, the reason why I call this the precious is because this is the Ring Nebula in um, in the constellation of Lyra. Ring, get it? Okay. So we've got this, and so the Ring Nebula is in the constellation of Cygnus, and Cygnus is smack dab in the Milky Way galaxy, or in the Milky Way. And what the Milky Way is, if you have been um, privileged enough to be in a very dark sky and actually seeing that milky band across the sky, you can. That is essentially the disk of our own galaxy as seen within that disk. And so, if one of the interesting things to do, even if you have a fairly low power telescope, or excuse me, low power pair of binoculars, is look up into the sky away from the Milky Way and just look in, and you'll see some smattering of stars. It's very pretty. And then just slowly pan through the Milky Way. Pan your field of view so that you pass through the Milky Way and then move to the other side of it. And what you'll see is, instead of just a cloud of light, and there were in the Milky Way in the ancient times was, some did believe that it was a solid or a cloudy object. But Galileo illustrated that if you magnify this thing in any way, that cloud separates out into individual stars. And as you pass the telescope, or the binoculars through the Milky Way, that cloudy band of the cloudy band that you see with your eye resolves into thousands of stars, individual little stars. And then you can move it through, and then so the number of stars in your field of view will drastically improve or drastically increase, and then it will drastically decrease as you move through the Milky Way. Now, this is to all the flat earthers out there. Particularly, there is this argument that has been going around about angular resolution and how it can be used to explain why objects objects disappear from the bottom up as seen on the horizon. What I will say is this is a prime example of the definition of resolvability versus detectability. The flat earthers will tell you that the reason why things disappear on the horizon is because of the angular resolution. Essentially, things get too small to see. That is not true. Things get too small to resolve, but you can still see them, so long as there is light rays or photons emanating from that object, and they can survive all the way to your eye, and your eye is sensitive enough to capture them. You can see them. And so the Milky Way, if with the unaided eye, so your eyes with the right drugs are about 8 millimeters in diameter, they only have a certain resolution limit, down to about basically an arc minute. Tuco was able to actually fully utilize the angular resolution of his own eye. That's insufficient to see the individual stars that make up the Milky Way galaxy, as seen from the Earth. But if you use binoculars, why do I not have a pair of binoculars? If you use a telescope, kind of like this bad boy, I love this. I love her. I will love her and call her George. Eventually, I will restore her at some point. But as you can see, this is bigger than this. And so, with a good pair of binoculars, which are about this size, the larger the aperture, the better you can resolve detail. And so, if I were to use this or a pair of binoculars to look at the Milky Way galaxy, I could resolve the Milky Way galaxy into individual little stars as opposed to this white blob across the sky. And so you can see the Milky Way. Assuming you're in a dark sky, you can detect the Milky Way galaxy with your eye, but you cannot resolve it for anything other than a cloud. If you get a larger instrument, if you use a telescope or a binoculars, you can resolve that cloud into individual little stars. And the reason why I bring all this up is twofold. One, and I've forgotten both, is twofold. One, this constellation or this object that I'm looking at, you all are looking at the screen, is in the Milky Way galaxy. So if you use the telescope, or if you pointed the telescope, you'd be looking at the constellation of Cygnus, which is right down in the middle of the Milky Way galaxy. So that's why you see as many stars as you do in this field of view, is because of that phenomenon. And as for the second reason why I went on that long digression, yeah, goldfish memory. I'm sure it'll come back to me. So, what we see here is the Ring Nebula. Now, Rob, what is the Ring Nebula? I'm glad I asked myself that question. The Ring Nebula is a planetary nebula. Now, astronomers are really kind of crap at naming stuff. For some reason, things just get named, and we just stick with it and keep going. The magnitude system, the brightness system of the stars, how we measure how bright stuff is, it's backwards. Thanks, Marcus. The Ring Nebula is, like I said, what's called a planetary nebula. It has nothing to do with planets. The reason why it's called a planetary nebula, or the reason why objects like it are called planetary nebula, are because with only a modest-sized telescope like the one I just brought out, this object would only appear like a small disk. And the only other things that appear like small disks through a telescope of that size are planets. And so, for whatever reason, and I think it was William Herschel, thanks, William, was the first person to coin that term. Now, the person who coined the term, I'm just going to default and say Herschel, although I could be very, very, very wrong. Herschel knew it wasn't a planet, because that's why he said it was a nebula. But it looked like a planet, but he probably didn't really think that it actually had anything to do with planets. A planetary nebula is the end stage of a star very much like our sun. So our sun, or a star of one solar mass, or a star that has a mass the same size of the same amount as the sun, will evolve. All stars evolve. All stars go through their own individual lifespan. Stars are born, they grow up, they get old, they die. A planetary nebula is the end stages of, it's an elderly star. It's an elderly solar mass star. So our sun, for example, is not going to go boom. It's not going to supernova and blow up. Only really, really massive stars do that. Only stars that are on the order of eight times the mass of the sun or heavier will, or more massive, I should say, will explode so violently. Smaller mass stars will pulsate. They will basically freak out, and they will just blow off their outer layers in a exciting but not explosive way. And so that's what this planetary nebula is the outer atmosphere of the star, which has been violently shaken off the surface and blown out into space. And in this, what's left over in the center is a white dwarf. A white dwarf is an object which has a surface temperature about 1.5 times the surface temperature of the sun currently, has the mass of about 1/2 of the sun currently, and has the size of the Earth. So very dense, very hot, but not very bright. because of the fact that it is very small. But we can see that this nebulae, or this ring, and this is just happenstance. Planetary nebulae are actually more dumbbell in shape, and to explain that would take far too long. So again, maybe another topic for a Rob World episode. But we're looking at this down the throat of this thing, and so it looks like a ring. Now, getting back to why I came up or was talking about this at all, was I was talking about the CCD camera and the fact that we take monochrome pictures of everything, but we do so in different filters. So so for example, this picture, pre-Ulti, I see that comment and I will address it in a moment. This picture is what the Ring Nebula looks like in blue. If you only looked in the blue wavelengths, that is what you would see. This is what you would see if you were looking in the green part of the spectrum. And this is what you would see is if you were looking in the red part of the spectrum. Now, let me see if I can pull up a... boom. That's what the Ring Nebula looks like, pretty much. If you were to actually be able to look at it with your naked eye, if you were close enough and you could fully resolve it with your eye, you could see it. That's kind of what it would look like. Maybe not as reddish, maybe not as dramatic, but that's basically what it would look like. I'm not sure people would say exciting when it will. Well, we won't be around. Basically, the Earth will not be habitable and may not actually exist well before about a billion. Well, I probably shouldn't give a number on that. At least a few 100 million years before the sun goes. The Earth will certainly not be habitable, and like I said, it probably will be enveloped by the sun itself. So it'll be exciting because it'll be like Doctor Who, where you're on a space station, and you can watch it from a distance in your cozy pad. Anyway, so this is the Ring Nebula. So this is what it would look like in blue, green, and red, or RGB, RGB true color. And so one of the things I plan on doing with the images that you can see is creating an image like that, is processing these images, getting rid of any sort of data artifacts. Like you can see here, there's this line which goes across. This is not a astrophysical phenomenon. This is just basically a defect on the chip. Oh yes, the oceans and the atmosphere will be gone probably a billion years. I want to say around 1 billion years, or about. So we are halfway through the sun's main sequence lifetime, so at around 4.5 billion years old. In about 3 billion years from now, I think that's really kind of where the end point of the Earth's habitability, any chance of it being habitable. That's where the oceans will boil off, the atmosphere will be gone, so forth and so on. And so I will be processing these images so that to get rid of these artifacts or these defects in the camera and the chip, and also there are other effects. And I will probably do a live stream at some point where I actually walk through this process of calibration frames that I take, and what those calibration frames mean, how they are applied to astrophysical images, and what they do to improve them. But my main point here, the thing I want to illustrate now, is the reason why we take monochrome pictures, why astronomers are interested in taking monochrome pictures as opposed to pretty images like that. It's because of there is a physical story that we are interested in learning. Let's close that out. And that story is found in the different parts of the electromagnetic spectrum. The electromagnetic spectrum, or the full spectrum of radiation across the universe, from radio all the way through gamma rays, light is basically just a energy transportation mechanism. It transports energy from point A to point B, be that radio, which is very low energy, all the way up to gamma rays, which is so high energy that if you get hit with it, you will die. You won't actually turn into a green rage monster. You will die. And that energy tells us what's physically happening with those objects. For example, if you're talking about in the infrared part of the spectrum, and you're talking about objects that are only around a few hundred degrees Kelvin, and or a few hundred degrees Fahrenheit. At this point, it's the conversion is pretty minimal. What we're talking about is dust grains. Basically, you're talking about something you can, if you were looking in that part of the spectrum, you can see basically the radiation coming off of interstellar dust, which is what makes up planets, for example. So if you're interested in exoplanetary formation, you want to look in that part of the spectrum. But if you're more interested in looking at supernovae or more energetic phenomena and some of these AGN that I'm talking about, then you might look into the X-rays or gamma ray part of the spectrum. But even within the optical, what we refer to as the visual part of the spectrum, which is a very, very tiny, narrow range, we can still get a lot of information. And that information deals with the composition of the gases in these nebulae. And so what we're looking at, like I said, if you remember, a planetary nebula is the outer envelope of a star, which is a main sequence rate, one solar mass or one solar mass-ish star. And it has gone through a chemical evolution from being primarily hydrogen and helium with a tiny little bit of trace elements to all the way to being primarily hydrogen and helium with a little bit more trace elements. And so, but because of the dynamic evolution of these stars, we have that we get all these gases, these heavier elements like oxygen and carbon get mixed into the upper atmospheres before it explodes. And so that's what you see when you're looking at an image like this. The red here, this orangey bit, or the orangey reddish bit, that's hydrogen gas. The reason why it's red is because hydrogen emits most of its light in the hydrogen part, or the red part of the visible spectrum. Or if you're talking about the visible range, hydrogen emits a lot of its energy at this temperature in the red part of the spectrum. The greeny bit, that's oxygen. The blue bit, I have to express a little bit of ignorance. I've kind of forgotten. I know I probably shouldn't. I shouldn't be ignorant about this, but it is what it is. But the point of what I'm making is that the red part of the galaxy or the nebula is colder, slightly colder than the bluer part of the image, and so we can look at. So not only can we so the first thing we look at is, all right, so what does this tell us? What does this tell us? This tells us what the temperature range of this object looked like from the outer parts to the inner parts. And based on that temperature profile, we now can understand what types of elements will be present to emit the different colors of light that we see, which allows us to look at the compositions of these objects. And so this is one of the things I find to be most fascinating about astronomy. One of the things I absolutely love about it is that 90% of everything that we learn in astronomy, and that is a completely made up number, but it's really, really high. Most everything that we know in astronomy, we get by analyzing light like this. We get pictures like this taken in various filters, filtering out the light, so we're only looking in very narrow ranges. And we have to develop tricks to understand what this light can tell us about these physical objects, because these are literally astronomical objects. They are at astronomical distances. They weigh astronomical. They have astronomically high masses. They are astronomical in size. Like, this thing is several times the size of the solar system. So there's no way to be able to put this into a laboratory setting. And the physics involved that describe these scenarios really can't. Some of it can be done in particle accelerators, but really there's no laboratory. This is the laboratory. These are the experiments that are going off in the universe. There's no way to recreate this on the Earth. So the only way to understand the universe at these scales is to look at the stars, to look at the astronomical objects, and we do that using these images. We do that using these things, and you can see. Well, let's go for the blue one. Let's compare and contrast the blue and red. First off, these were taken using the same exposure times. So the camera's shutter was open for the same amount of time for the blue image and the red image. So the differences that you see, there are two things that account for the differences that you can see. The camera itself is not as sensitive in the blue part of the spectrum as it is in the red part of the spectrum. That has to do with the physical properties of the filter, a piece of glass that the light moves through, and also the detector itself, the silicon chip that it's exposed to. And so the blue image is going to be fainter than the red image simply because of that. But the other reason, and this is you can still bear this out, is the other reason is because of those color changes. The outer, as you saw in the three color image, the outer part of the ring nebula is red, whereas the inner part is blue. And so we would expect that if you were to compare, like I said, if you compare and contrast these, let's bring this over. Let's make these smallish. You can see that the ring nebula in the blue is slightly smaller than the ring nebula in the red. Hopefully you can see that. I could quantitatively measure that for you, but hopefully you can see that without too much trouble. And apologize. Like I said, allergies. And you can, so it looks physically, it's physically different. And also you can see that in the blue image, it's more of a blobby sort of object than in the red. In the red, it's a clear ring with an evacuated center. In the blue image, not as much. You have the blue part of the interior part of the galaxy, or excuse me, of the nebula is brighter because it's bluer, because the gas there is still pretty hot from having been ejected off of the star. So yeah, so that's why we take images the way we take images. All right. All right, let me shut all of this down. Like I said, at some point I will do a live stream that where I probably the Andromeda Galaxy. I have a lot of images of the Andromeda Galaxy that I want to process, and the Andromeda Galaxy is so large with respect to our telescope that I actually had to do. Well, I have to do what's known as a mosaic. I've taken images of parts of the galaxy, and then I have to create those images, or I have to put those images together, and then I have to put all of those images to make one big, larger mega image. And so I will probably do a live stream where I stumble my way through that. And when I do that, I will talk about the various calibration images that I use, like dark frames, bias frames, flat fielding, that sort of thing. There will probably be a lot of gnashing of teeth and swearing and things of that nature, because image reconstruction is, I don't want to give people some, there's a certain amount of art to it. Uh, Flat fielding is a bit black magic. I don't want to give science deniers any ammunition. I'm not saying that you should do that. Flat fielding negates the value of these images, but in order to do it properly, if you want to get really good results, to be able to flat field your images correctly that's probably the biggest hurdle in terms of calibration. Taking the bias pedestal off, accounting for dark current, those are fairly rudimentary, pretty easy things to do. Flat fielding properly, that's a more sophisticated technique. And so yeah. Oh, all right, it's parked. Okay, so I'm going to disconnect. And I'm going to shut this down. And I'm going to I'm going to park the dome. Oh, Rachel, you're here. I didn't realize that other people were still watching. Great. I'm glad you learned a lot. Can you see? And just because I want to do that, can you see the Hubble telescope with this telescope? Yes, but it's really hard to do. So the Hubble telescope is not moving at the sidereal rate. So the Hubble telescope is moving against the background of stars. It's moving again, so it's moving faster than the stars appear to move across the night sky. And so, if you were to look at the Hubble, if you were able to get the Hubble telescope in the field of view, then it would quickly move out of the field of view. And what I mean by field of view is the part of the sky that you were able to look at using the telescope. The other tricky bit is that our field of view is fairly small in that it is around it's 25 arc minutes square. Now, what is an arc minute? An arc minute is a subdivision of a degree. So the entire sky is 360 degrees. The sky that we can see from one horizon to the other is 180 degrees. The full moon is half a degree in size or in diameter. And so, or it is 30 arc minutes in diameter. You can take a degree, and if you split that into 60 equal width segments, each of those segments would be 1 arc minute in width. And then you can further subdivide that. Each arc minute can be subdivided to 60 equal parts, and that is 60 arc seconds. So the tricky bit is we're looking at a field of view roughly the size of the full moon. So a fairly small area on the sky. And so we'd have to, the chances of us having the Hubble telescope pass through our field of view are very small to begin with. Not astronomically rare, but small. But it would also be very, very quick. The difference in speed between the Hubble Space Telescope and the background stars is very high. I don't know what that number is off the top of my head, but it's very high. So really what you would see, depending on how long you were exposing or how long you kept the shutter open, you would basically see a streak across the image. So you wouldn't be able to get a really great image of the Hubble telescope, but you would be able to see it. So yeah, hopefully that answers that question. All right. So I'm going to shut that down. This is part. Shut that down. And I'm then going to, yes. All right, I'll bring this over here. Ah, that's how you get the inception window. That's cool. All right. Okay, that's pretty much all I had for this stream of tests. Thank you, everyone who has watched either live, Rachie, Priolti, Tusk, for the great comments that you've made. Thank you, like I said, thank you all for watching me ramble on incoherently. Well, hopefully somewhat coherently. And yeah, so the next time I do this, it'll be a little bit more planned. So I'll have a little bit more, be a little bit more streamlined. But I can hang out for 15 minutes if anyone wants to show up, or Rachel, if you have any other questions that you would like me to pontificate on, and I can do that as well, or not. So maybe not 15 minutes. It would be really weird just to kind of stare at the camera for 15 minutes. So how you doing, Rachie? I have to say I have not been over to your channel in a while, so and I apologize for that. Any chance you'll be able to make it when you can open the dome? Yes. So the reason why I did not open the dome today was because of the fact that we just had a rainstorm pass through, and I am hyper paranoid about opening a telescope when there's even the remotest possibility it could get rained on. But in the future, I do plan on looking at, granted, weather, as we all are familiar with, is unpredictable, reasonably unpredictable. And so I will, as best as I can, I will try to get these streams, or to schedule these streams so that the night is clear and that I can open up the telescope and actually take images of the night sky. One of the telescope is at, so I work for George Mason University, and one of the things I can say is over the summer we do not do this, but during the fall and spring semesters, starting in or about late August, early September, we will have public nights every couple weeks. And so what we have a Zoom link. We did this during the pandemic. We will be doing in-person shows in the fall, but I believe our goal is to still have a virtual component, and so I will be putting or promoting that more so than I did last spring, and so I will let folks know that what the Zoom link is, and so people can come on. And if for whatever reason I am not able to actually show the night sky, to actually actively image the night sky using our telescope, sometime during the fall or fall months, that everything will cooperate, and you will actually be able to see what the sky looks like using our telescope. So yeah. So let's see. Well, thank you. I hope it was coherent. I worry about that a little bit. I kind of get a little bit scatterbrained. So if you have, so there are two things to consider in terms of looking at satellite work. Actually, hold on. Let me see if I can do this. Oh. Let me put this over here. Let me see if I can share my screen. Am I sharing my screen? I have no idea. I was sharing my screen. Okay, probably. Tweak. So can you see that? Is that image up? I'm hanging in there, Rachie. I am, as I like to say, to steal the catchphrase of Amanda the Jedi, I am doing mostly okay. All right, so this is one of the reasons why I think Elon Musk is kind of a D-bag, because of this nonsense. This is Starlink. So you've probably all heard about Starlink, which is an admirable project. I am fully in favor of getting internet access to remote areas or rural communities. Fully in favor of it. But it needed to be thought out a little smarter than this. And so what we're going to be facing in the coming years, what astronomers are going to be facing in the coming years, is, let's see if I can make this bigger, is what we're referring to as constellations of satellites. And so this is one of the premier telescopes. This is run by the Europeans, Gemini North and South. These are 8-meter telescopes, so just slightly less smaller than the Keck. These are premier research instruments. They are Gemini South is in the Andes Mountains. It is 14,000 feet above sea level. I mean, there is a lot of money and a lot of research time involved in putting these things together. And so it's a shame when our observations can end up looking like this. This is a Starlink satellite passing through the images of the field of view. I honestly don't remember what the field of view for Gemini is. It's probably on the order around half a degree or so, maybe smaller. But you can see that these satellites are moving much faster with respect to the background stars. And so for a 1-second exposure where the camera is open, the shutter is open for a single second, that is sufficient enough time for that satellite to pass through that image, and it'll basically be imaged as a streak of light as opposed to a single point. And so one of the things that we're going to have to contend with in the astronomical community is Starlink isn't going to be the first one of these constellations. Jeff Bezos is putting out his own constellation. I don't know what it's called, but Amazon is putting out its own satellite constellation. And so there are going to be thousands upon thousands of these commercial satellites that are out there that are going to just be cluttering the night sky. Now, what I'm irritated with is there are ways that you can mitigate how bright these things are. And it seems to me that Mr. Musk did not really consider these. He said that he reached out to the astronomical community and worked with them as to how bright these things were actually going to be, and he was surprised by how bright they actually are, and yada yada yada. He also said he could paint them. He could fix this by painting them black, which is just ridiculous. Anyway, I could go off at length about Mr. Musk. Anyway, is it the end of astronomy from the ground? I don't know if I would be that cynical about it, but it's definitely something that we're going to. It's definitely getting to the point that there's going to have to be some kind of government oversight, where governments have to come into, where governments have to step up or should, I should say. I would like governments to step up and be able to regulate just how bright some of these objects, these satellites, can be when put into orbit. Now, I will say that the satellites are not always going to be this bright at all times, because these satellites are not putting out a lot of light on their own. The light that you see in that image is reflected light, so they have to be in a proper orientation, very much like the moon. In order to get reflected light off the moon, the satellite has to be in a particular location so that the sunlight hits it and then reflects back directly towards us. So if the satellite moves out of that or moves into the shadow of the Earth, then we're not going to be able to see it. So it's not as bad a picture. It's not as grim as a picture as I might be pointing out, but it's not going to be great either. So who knows? But yeah. So in terms of the Hubble space satellite, if you're talking about a small pop-ups, if you're talking about a small area, then a small field of view with things that are moving very rapidly, then you're going to see them as streaks, but the chances of that happening are fairly rare. I've actually, although I no longer have the image, so I can't prove it, um, the most exotic thing I have seen through a telescope is a bat. I was an undergraduate at the University of Florida, and a bat flew across the field of view of our the 30-inch telescope down there, and so we actually got an image of this weird shape moving across. It's kind of bizarre, actually. So yeah. Okay. Are there any other questions folks have? Again, thank you for being here, and I will be posting this onto the tubes. And all right, peace out, everybody, and yeah, I will see you all again. The next time I stream, I will it will be planned, as I said, or as I keep threatening. And so please be sure, if you haven't subscribed, please do hit that bell, all that kind of good stuff, and you'll be notified the next time I plan on doing one of these live streams. And in the description, I will let you know. Although I think that the time of the stream should be an indication of whether or not I will be looking at the sky or not, but or as opposed to talking with someone about just astronomy or science education and so forth. But I will put in the description, let folks know that whether or not it is my intention to actually look at the night sky actively. So, as always, no matter how dark it gets, always remember, you're stardust.